Today we are happy to have Surena Hozoori from Brandeis telling us about strongly adopted contact geometry of Anosov reflux. Thank you so much for the introduction. I'm very happy to be here. It's my pleasure to speak for this great audience. So I would like to thank the organizers for the invitation. Today, my goal is to talk about some contact geometry framework for the study of Anosov flows in dimension 3. Anosov flows were introduced in the early 60s by Dmitry Anosov. They're known to be the prototypical examples of chaotic dynamical systems, and thanks to their very interesting rigidity properties, they're known to have very deep and subtle kind of connection to the topology of the underlying manifold. Today, I'm planning to kind of advertise some sort of contact geometry approach in the study of these objects. So this is a three-dimensional talk. So during this talk, M is going to be a closed-oriented connected three-manifold. X is going to be a non-vanishing smooth vector field on M. And this is the notation that I will use for the flow generated by this vector. And the first definition will be for our main objects here, which are kind of Anosov flows. So we call the vector field or the flow generated by this vector field Anosov if there exists some continuous flow invariant splitting of the tangent space into three line bundles. One of them is going to be the direction of the flow, and there are two other line bundles I call ES and EU, calling them stable and unstable line bundles. And the property that I need on these bundles is that if I look at the vector field in, let's say, in the EU direction, and look at the action of the flow on this vector, I will see, I will see exponential expansion with respect to some node. And if I take a vector in the stable bundle and look at the push forward of this vector kind of along this flow, I will see some sort of exponential contraction with respect to some norm, where like this, I have A and C as positive constants, and of course I need a norm on the tangent space to kind of make sense of this. The kind of very schematic picture, immediate schematic picture I can draw for this object would be probably something you can imagine for anything hyperbolic, which is, you have some sort of contraction in one direction. So think of the flow kind of pointing outward on the board, and you have this other bundle, which is U, and that will basically force what's happening to the rest of the tangent space. This is kind of like a schematic picture. But if you want to kind of pause and meditate on the definition for a second, you notice that what this definition is kind of telling you immediately is basically eventual expansion and contraction. What do I mean by that? By that I mean that suppose in this definition this constant A is less than 1. So the kind of lower bound that I get, so let's say this is 1 and this is my A, so let's say if A is less than 1, the lower bound that I get for this my expansion is going to look like this, right? So this is y equal to b A e to the power of c. And respecting this kind of lower bound means that I'm allowed to have a little bit of contraction before being forced to expand, right? So that means that this definition tells you about eventual expansion, not just immediate expansion. However, there is, there is some averaging technique that I can use, and basically by some appropriate notion of averaging the norm along the flow lines, I can basically construct some norm where this immediate expansion and contraction is happening basically immediately. So there is some averaging technique which is due to Holmes, and it's kind of popularized in this famous book of Hirsch-Q, which tells you that immediate expansion, there exists some norm such that you have immediate expansion. And if I want to kind of put that in this definition, that means that I can
find some norm where this lower bound when A is equal to 1. So basically, when A is equal to 1, this would be my like lower bound, and then because this other kind of function here, which is kind of telling you about the norm. So this was basically x star t u this. So now if I want to respect this kind of purple kind of lower bound, I will be forced to immediately kind of expand. And the norm with this property is called adapter. This is equivalent to having A equal to 1 in the definition. Okay? And the adapter that you see in this picture is exactly the adapter you see in the title of the talk, which means that I'm planning to kind of give you some sort of contact geometric interpretation of this process. And the way that you should think about this is that this is some technique that helps you localize the kind of information about the expansion and contraction of the norm along the flow lines. Yes.
So by norm, you essentially just mean Riemannian metric, right? Or
yes.
it's okay, it's just Riemannian. And then it seems being Anosov kind of doesn't care much about which metric you pick. Is that correct?
Yes, that's correct. So any kind of, if it's a closed manifold, any kind of norm would be kind of equivalent. So yeah. But with this property, you can kind of with this norm, and with this technique, you can localize and see the expansion contraction.
And this norm is unique, right? As soon as you say A equals 1, there's just, if there is, there is. I mean, you say there is by averaging, but then.
No, I mean, it's not necessarily unique. You can do, if you have a norm with this property, you perturb it, it stays. Yeah. So now that you if you believe this, then that would justify the schematic picture that I sketched. And in fact, a more honest picture would be to imagine this any flow line in the intersection of a pair of foliations. So here I have one foliation, other foliation. And if I look at this, any kind of piece, any segment of the flow line, it is staying on the intersection of two foliations. On one of them, you see the nearby flow lines kind of being sucked into the center flow line. And on the other one, you see like the flow lines kind of staying in the center flow lines. And this is here, these are called basically stable and unstable, weak stable and unstable foliations. And here, like the tangent space is given by kind of pairing the flow direction with these kind of line bundles that we have.
Okay. So having Anosov gives you two foliations, or having two foliations?
No, having Anosov will give you like two foliations, because if you pair these line bundles with the flow direction, that would be an integrable kind of foliation. That will be an integrable plane field. And it's not immediate, but it is uniquely integrable. A priori is only C0, but in fact, with some work that you can show that these are C1 kind of plane fields. But you need that would be kind of a bit non-trivial, because notice that the kind of splitting that I mentioned in the definition, that was just a continuous C0 kind of splitting. And the remark about this is that you should, even though this gives you some sort of local visualization and picture, you shouldn't really take this too seriously as a local model, because this kind of splitting and these plane fields are in fact determined by the long-term behavior of the flow. So if you kind of perturb the flow in a neighborhood, all of these kind of foliations will be kind of changing and in the entire kind of manifold, and you can't really in this situation typically expect more than C0, but here at least for the plane fields we have C1. Okay. And the other remark is that, as I mentioned, these are only typically C1 kind of plane fields. So these are remark in general. These are C1 kind of foliations. And there is a whole kind of theory of trying to understand the regularity of these foliations and these invariant bundles. A lot of them going to the work of Hirsch-Shuba and some work of kind of Boris Hasselblad. The other kind of thing that we might want to have in mind is that this splitting is also not necessarily orientable. So, but that's not a problem if you can go to a double cover and fix it. So, what are some examples of these flows? I start there.
Question.
Yes. Right. Yes. So I hear the word on the pseudo and also quite often before. I was wondering how to string that together. Yes, so pseudo and also would be adding one more kind of basically allowing some kind of singular orbit. So here any kind of flow lines is sitting in this kind of intersection. But a pseudo and also you're kind of allowing kind of more than you have finitely many kind of orbits, periodic orbits where you have some kind of you have more than basically two kind of foliations. Okay, but here I'm talking about Anosov, I'm not really allowing the pseudo. So the two kind of classical examples.
Is the point about pseudo-Anosov is that they're easier, their existence is easier to prove, right?
Yes, I mean they're kind of their theory is much more topological. Their existence they're kind of much more abundant, but their dynamics, especially from the viewpoint of smooth dynamics, can be kind of more complicated. So the two classical examples are one of them is suspension. So if you just consider C2 as the kind of R2 over Z2, and if you take some matrix in SL2Z, where it's a hyperbolic matrix in the sense that you have two kind of real eigenvalues with one of them bigger than one, the other one less than one, then you can use this to kind of define a suspension, right? In the sense that you consider basically vertical flow lines, and then use this map to kind of glue the floor and the kind of ceiling. And if this kind of automorphism of the torus is hyperbolic, that will be translated into the suspension flow being Anosov. And the other kind of famous example, which is the one Anosov started with, is that if you have a hyperbolic surface, then the geodesic flow on the unit tangent space, basically Q1 sigma, so the three manifold is also the hyperbolicity of the metric will be translated into the anosovity of the flow on the unit tangent space. And in fact, with this kind of regularity remark having in mind, it's known that these are the only examples where these foliations are better than C1, they're C2. So there is some sort of rigidity kind of going on here, that the moment that these foliations are C2, all of a sudden you're in one of these two examples, which are called usually like algebraic kind of Anosov flows. And in fact, around like 20 years, it was an open problem that whether there exists any other Anosov flows. Their construction was not known at the time, and it took around 20 years until Thurston came along and kind of introduced a lot of like surgery theoretic kind of approach. And for now, we have many more examples.
So there were only these two examples of the 20 years?
For 20 years. Yes. For 20 years, these were the only two examples. But in the early 80s, Thurston introduced new kind of surgery theory, kind of surgery constructions, and right now we have many kind of different surgery kind of constructions. One of them for Thurston handle, one of them Adam Goodman, the other one by Full and Hasselblad. Each one of these constructions were kind of done for some specific purpose and kind of open problem. But now we know that these kind of flows are more kind of abundant than we initially thought. We have many kind of infinitely many hyperbolic manifolds, for instance, with an admitting some Anosov flows, but all of them, these foliations have like low regularity. So dealing with low regularity is something that we need to really deal with in this context. And in fact,
so 1 and 2 are essentially two-dimensional examples. The 3 are three-dimensional.
Yes, in some sense we can think about it. I mean, we are using some two-dimensional. Yes.
Yeah.
The one is.
No, here I'm constructing the suspension.
Is multiplying that by R, like an interval, and then gluing.
Yes, so think
Sorry, otherwise.
But they are kind of both coming from 2D data.
Exactly. They have some
They're higher dimensional.
Yes, so the very same kind of construction for any kind of hyperbolic manifold, on the unit tangent space, you will have a Anosov flow. And similarly, if you have a suspension with this kind of,
Those are compatible.
well, not necessarily. I mean, it's not super clear what's the kind of analog of this contact geometric approach in higher dimensions. Well, focusing dimensions.
And the Thurston thing probably is super three-dimensional.
Say it again.
I'm saying, and Thurston's approach is probably super
Very
three-dimensional.
three-dimensional, exactly. But one thing is that we know a lot in low dimensions, in dimension 3, partly because of the application of these Todd foliations, because the foliations I'm mentioning here are Todd foliations, and the topological theory of them is kind of used in this study. One important thing that makes this kind of special for like topologies is the fact that these flows are structurally stable. And that means that if you start with some Anosov flow, and basically C1 perturb this flow, then you get a new flow, which is not only Anosov, but also there exists some homeomorphism of the kind of manifold on the underlying manifold, sending orbits to orbits. Which means that by just the perturbation of the flow, you can't really produce a new flow which has like fundamentally different orbit structure. And if you think of this as a kind of equivalence class, this is called orbit equivalence. That means that the space of Anosov flows modulo this this kind of equivalence relation is a discrete set. And something that topologists like to do is to kind of classify discrete sets, right? So the big question in the field, which kind of also motivated Thurston, is to classify this space. Basically, classify all the all possible, given some three manifold, classify the Anosov flows on this three manifold modulo, this kind of equivalence between them, which tells you like at the level of topology, the orbits have the same kind of structure. So classify this space.
But so one doesn't know finite, that's for any three manifold or?
No, so that's what I wanted to mention. So it turns out that we know very little about this kind of classification question. So let me first tell you like what we know, which are all of them are pretty old. So what do we know? Or like if you can try to classify these things, or more generally, you can try to understand the kind of homotopy type of this space. It turns out that we know very little about like any kind of classification question for these flows, but some things that we do know, all of them are kind of old. For instance, we have a classification of ciphered fibered manifolds. And the classification is that, if you have an Anosov flow on a ciphered fibered manifold, it's virtually equivalent to a geodesic flow, the example I gave you in the beginning. And other than that, we don't know classification on any three manifolds.
What does that mean? It means that you can think about some, so if you have ciphered, so you're thinking your manifold is fibered over a surface, and then the Anosov flow would be.
If you can go to some finite cover, where on that finite cover, that the flow that you're kind of lifting would be equivalent
to the
exactly. But we don't have classification on any other three manifold, and we also have some obstructions. One of them was like due to Thurston and Plante, which tells you that the pi1 of a manifold admitting an Anosov flow should have exponential growth, which essentially means that the pi1 should be quite large. And that means that, for instance, no Anosov flows on S3 on T3 Niels manifolds and so on. So you could have a fairly large kind of pi1, and also kind of more recent results from like Higgins-Floor homology tells you that you can't have basically an L space. So even like the Higgins-Floor kind of invariance should be also kind of relatively large if you want to admit some Anosov. And this is an obstruction for the existence of a Todd foliation, basically that was kind of underlined. But other than these kind of results, we basically don't know anything. We don't have any three manifold other than the ciphered ones where classification is known. Given some hyperbolic manifold, we don't really have any way of telling whether it admits some Anosov flow or not. As far as I know, we don't even have example where there is more than one Anosov on the same three manifold. So a lot of things are kind of quite unknown. One of my favorite kind of conjectures is the finiteness conjecture, which tells you that any three manifold fix some like three manifold, then there exists finitely many Anosov flows. And that's also kind of not known. So we have a lot of like open problems, and most of the topological methods are coming from the application of Todd foliations and geometric group theory. But as you see about these types of questions, there haven't been that much progress.
What is the motivation of the conjecture? Is there a reason that you wouldn't expect infinitely many? The discreteness is probably one reason, but is there any?
To have infinitely many. So
Yeah,
there are
what's
many.
the motivation.
So there are many constructions that for any n you can kind of construct like a three manifold admitting n. Kind of like Anosov flows, you can take.
You can take limits of the three.
But yeah, but the problem is that if for similar objects, I will mention this in the contact geometric approach. A lot of times, these types of finiteness results are kind of like, in some sense, natural, kind of frequent in like low-dimensional topology, and there's a very kind of topological flavor here. So a lot of people would expect, we have finitely many of these kind of orbit kind of structures. But it's not known, so that's why it's a conclusion.
What about higher dimensions? Would one expect finiteness, or is it?
The method, the techniques and tools we have are kind of much less because we don't have like this whole nice theory of Todd foliation. So much less is known in higher dimensions. So what is the contact geometric approach? So let's see. High contact geometry. So I would like to advertise this theory and kind of reformulate this theory, not in terms of these invariant bundles, but in fact, in terms of these two other plane fields that kind of show up here, like kind of as the bisectors of these kind of invariant bundles. So let me start with the definition. You have a one form alpha is called a contact form if alpha is the alpha, which is a three form, is actually a volume form on your three manifold, and if your manifold is oriented, so if it's a positive volume form, we call it a positive contact form, and if it's negative, we call it a negative contact form. And the contact structure is a plane field, which is basically the kernel of such one form. By Frobenius theorem, that means that the contact structure is basically a maximally invariant plane field. And if I want to kind of write down an example, I can easily do so on R3. This is called the standard contact structure on R3. You can define alpha as dz minus y dx. And if you look at alpha with d alpha, it's easy to see that's the standard volume form of R3. And if you want to kind of draw a picture of this plane field, the kernel of this one form, you see that at the origin you have dz, so you have some sort of horizontal plane field, but as you kind of, and the y direction is always in the kernel, so it's always tangent to this plane field, and if you go in the y direction, you see some form of rotation of this plane field. So as we kind of move here, you see some sort of rotation of this plane field, but there's two ways to kind of rotate. Here you have what we call left-handed rotation, which tells you about this contact form being a positive contact form, but there's another way to rotate, okay? And the kernel is also invariant in the X and Z direction. So this is a picture that is kind of being invariantly kind of repeated. So this is the contact structure, and it turns out that this is a local model for all the contact structures. So we have this Darboux theorem, which tells you that any, let's say, positive contact structure locally looks like this.
The positive means we have an orientation.
Yes, my three manifold is oriented.
Compare the volume from the
Exactly. So I'm assuming my manifold is oriented. So if I compare this volume form with the orientation of my manifold, this is either positive or negative. But it turns out that all the positive contact structures locally look the same. So this is somewhat an honest picture locally. So if it's the first time you're seeing contact structures, the useful way of thinking about them is to think of them as rotating kind of plane fields. And also we have Gray's theorem, which tells you that any homotopy of the contact structures is induced from ambient isotopy. So in some sense, by just perturbing, like deforming a contact structure through contact structures, you can't really produce any new contact structure. And I would kind of interpret this by saying that these are kind of geometrically stable. And this should rhyme with the properties of kind of Anosov flows where you have some sort of dynamical rigidity and you have like some sort of dynamically stable structures. And you want to kind of use these kind of geometrically stable structures to describe those kind of dynamically stable kind of dynamics. One more piece, which is something that I need.
I think the other one is better.
This one?
Yeah.
Yeah. So it's pretty.
Yeah.
But anyways, another kind of useful kind of definition is that there is some sort of dynamical approach to the study of contact structures using a vector field, which is what we call a Reeb vector field. And that is to say that if I pick some contact form, then there exists a unique vector field R alpha such that it satisfies basically alpha of R alpha is 0, and also this vector field is in the kernel of D alpha. Okay, so there's a unique vector field with these properties.
Did you mean that's the one? Yeah, that's one.
Yes, you're right. Thank you. So that means that if you think about the context, the condition, you can check that this is equivalent to say that the kernel of alpha and the kernel of D alpha as a kind of line bundle, they're transverse. And this Reeb vector field is the unique vector field that you can choose in the direction of the kernel, which is normalized by alpha. And this gives you some sort of dynamical approach in the study of contact forms since early 90s and the work of people like Hofer, Wysocki, Zender, Hutchings, and other people. It's known that these flows have like very deep connection to the topology of the underlying manifold. So how does that relate to Anosov flows? That is mainly due to an observation of Mitsumatsu and Eliashberg-Thurston in the mid-90s. Which tell you that if you have some Anosov flow, this Anosov kind of vector field lies in the intersection of a pair of positive and negative contact structures. Like positive, negative, positive. Writing this as a proposition because to kind of indicate that this is quite actually easy to see. So if you just remember the schematic picture for Anosov flows,
So you mean the plane associated to those, what do you mean by intersection?
so these are two plane fields. They're kind of
plane.
transversely intersecting. And this is very easy to see because all you need to do is to take the bisectors of these two kind of invariant plane fields. And the rotation that the action of the Anosov kind of action on these plane fields, this is forcing some sort of rotation on these plane fields. And you can, it's an easy exercise for the Frobenius theorem to convince yourself that this is exactly the same condition you need for the contactness of this rotation you see is the same rotation you saw in the definition of contact structures. So it's very easy to see that you have two kind of plane fields, positive, one of them positive, because one of them is being rotating in one direction, the other in the other direction, and here your kind of flow direction is lying in this intersection. If you are very optimistic, you might hope that, okay, maybe this is the only condition that I need. Maybe this contact geometric condition kind of characterizes an Anosov flow, but that turns out to be a little bit far from truth. But nevertheless, this bicontact condition, we call this pair. So let's say call such pair a bicontact structure. It turns out that this having a bicontact structure still has some dynamical kind of interpretation, which is some weak notion of hyperbolicity. So some generalization of Anosov flows, which we call projectively Anosov. And in order to see that, you should see that, okay, if you have a flow in the intersection of a pair of positive and negative contact structures, this rotation and some contraction argument will tell you that there is some invariant plane field in the middle. And if you go backwards, you can convince yourself that there is also some invariant plane field here. So you do have two invariant plane fields that we call them E and F, but you also have something more because this rotation, if you think about this angle, this rotation is kind of increasing this angle. And if you're increasing this angle, you're kind of increasing this ratio. Okay? So you have something which is a relative expansion of one of the bundles with respect to the other one. So if I want to kind of reformulate this proposition, you can see that being in this such transverse intersection is equivalent to having two invariant plane fields. Let's write them as the splitting of a normal bundle of the flow into two line bundles, such that if you take a vector in one of them and look at compare it to the expansion of a vector in the other one, this ratio is kind of expanding. And these flows are called projectively Anosov, or flows with dominated splitting. We call them projectively Anosov flow because they have a similar kind of action on the projectified normal bundle of the flow, basically, similar to an Anosov flow. And these are also called flows with dominated splitting, and this condition turns out to be at the cornerstone of the stability theory of like in hyperbolic dynamics. So a lot of the stability features of Anosov flows are really coming from this domination that.
So I understand, I understand that you mean being Anosov is not equivalent to this condition, but what you did was that you changed the Anosov condition to something that it would become equivalent. Yes. But couldn't you add some extra conditions on the contact structures you had to make that work?
You're talking about my main theorem.
Okay.
So
yes.
That projectivization is a real projective line circle.
Yes.
So should I think there's a flow on that circle with some property that says it's projectively Anosov, not the property that says it's Anosov?
Yes, so basically, if you think about this projectified kind of bundle, what you have is that you have like 4 kind of points, or like 2 points if you're kind of projectified, and you have this kind of action on this projectile.
It's effective line, that's 2.2 fixed points.
Okay, yes, so you're right. This is double cover of the projective line if you want. So this is basically, you have 2 points and you have this kind of action on this.
Right. But that's projectively also.
Yes, that's projectively on us.
What's an additional also?
Pardon me?
So what additionally has to hold the anosov?
Yes, that's my main theory. So I can add some, that's the point. I can
Just
add,
from the definition.
also from the,
Linear space.
from the definition, you need some, this is about relative expansion.
Right.
Okay, but you need absolute expansion. So for instance, you can take, you
The
can,
flow looks the same. Effective line.
exactly. So this is a flow where it has a similar action to an Anosov flow on this projectified kind of quantum.
Linear.
Yes. So you can have a, let's say, periodic orbit when you have like expansion in both directions, but one of them is going, one of them is going to kind of dominate the other one. If I want to do a tiny kind of quick computation, I think it might be useful. So if I want to kind of look at this context form, so one thing before like this, let me say that these flows are actually abundant. So unlike Anosov flows, you have example on any three manifold, even sphere, torus, these kind of manifolds which don't admit any Anosov flows, because all you need is basically take two contact structures and make them transverse, and that's not like super hard. If I want to do a tiny kind of computation, let's say we're in the Anosov kind of situation. So let's say this is, if I look at some contact form for this contact structure.
That's easy in dimension 3 though, right? Not in higher
Yes.
dimension.
This is, everything is dimensions.
The theorem is also 3-dimensional, right?
Yes.
Okay.
Yes, this is three-dimensional. Yes. So if I take a contact form, I can, using kind of linear algebra, I can split it into two two kind of one forms. One of them whose kernel is this invariant kind of plane field, unstable plane field, and the other one the stable plane field. So let's say this is defined by saying that the kernel of alpha u is, let's say, ES plus X. And if I look at this also defines some sort of norm on the unstable bundle, right? So I'm defining this kernel and also gives you some norm. Because if I want to write things in terms of contact form, I need to write it in terms of this differential kind of form, right? And if I look at the lead derivative of this, is preserving the kernel. So the lead derivative would be some multiple of the form itself. And this kind of function showing up here will tell you how much the norm is expanding and contracting, right? So this is what we call an expansion rate. So the idea is that any contact form will induce two norms on the unstable and stable bundles. And these norms will give you some sort of expansion information. And I can do the same thing for the other bundle. So this one would have the other kind of plane field as the bundle, and also I can basically define some sort of norm. And if you think about the contact condition for this contact form, you can easily see that this is the same as RU minus RS times some of the volume form. So in some sense, the contactness is exactly the relative expansion of the norms, because this being positive is equivalent to RU being bigger than RS. So you have the norm that is inducing on these plane fields satisfies some sort of relative expansion. Okay? And that also means that you have some Anosov flow if and only if you have a norm or a contact structure inducing these norms where this RU is positive and RS is negative, which corresponds to having absolute expansion in the unstable direction and absolute contraction in the stable direction. Okay? And also notice that the norm satisfying this condition would be adapted, because this is happening as a differentiable kind of level, a derivative level. So you have immediate expansion if this RU is positive, and you have immediate contraction. So for some adapted. No. Okay. So a natural question is that you have some class of dynamics for which we have a purely contact geometric kind of definition in some sense, right? So you have a projectively Anosov, and this is equivalent to this bi-contact structure. Or like if I want to draw a picture, let's say this is a picture. And the natural question is that, is there some sort of purely contact geometric definition which makes this a structure kind of like equivalent to being Anosov? It turns out that there are two ways to kind of answer this question. One of them is using like Liouville geometry in dimension 4 and kind of add some additional structure to a bi-contact structure to make it equivalent to a definition of Anosov flow. But there's also a three-dimensional way of thinking of answering this question, which is based on the Reeb dynamics of these two contact structures. And that's the one I'm going to talk about today. So the Reeb dynamical approach. So I start with a very kind of elementary observation that if you have a like contact form defined the way I was kind of describing, if we just look at the Reeb vector field of this kind of like contact form and pair it with the direction of the flow, like any other direction, you should get kind of 0. And that tells you something about the expansions of these norms in that direction. And the kind of consequence is that you can basically see in that picture where the Reeb vector field is. And this Reeb vector field is going to be in the span of the flow direction and something that I can write like this. So this is my ES, this is EU. Let's say given the norm induced from this contact form, let me call ES and EU as the unit vectors. And the Reeb vector field, let's say this is my contact form, this is the kernel of alpha plus. And the Reeb vector field, I can basically see where it is in this picture. I'm guessing maybe one of these should be, if RS is negative. So I think this is.
So here X is
Yes, X is kind of pointing in this direction. The message is that looking at this kind of expansion information, I can see where the Reeb vector field is in this picture. An immediate kind of consequence of this is that if you have a like projectively Anosov flow, so you have a bi-contact structure, then X is Anosov, because Anosov means that this RU is positive and this RS is negative, or at least there is some contact form where this is happening. But that's happening exactly when the Reeb vector field is in these two quadrants. But those are the coefficients over there. So if and only if R plus is included in the second or fourth quadrant of this picture. And in fact, that means that the norms inducing from this contact form are adaptive, because that's when RU is positive and RS is negative, and because this condition alpha plus being adaptive, because that's equivalent to the norms inducing from the induced from this contact form being adaptive. So this is kind of nice. It has some consequences. The downside is that this is not purely contact geometry, because I'm kind of referring to these bundles, second and fourth quadrant. But before kind of giving you the better kind of theorem, it's good to notice that this has at least some consequences. For instance, that means that if you have an Anosov flow, this Reeb vector field can be taken to be transverse to these kind of foliations, which are path foliations, which that would imply that this contact structure would be hypertight. Hypertight means that it wouldn't have any contractible periodic orbits. The reason it's important for us is that there are kind of not that many contact structures with this property. So that would rule out a lot of contact structures from kind of showing up underlying some Anosov flow. So contact structures showing up in this construction are special kind of contact structures. In particular, with some work, you can show there are finitely many of them on any three manifold, which is something that we need in the kind of finiteness conjecture. There are other corollaries.
So is it about one of them or both of them? Should be
Both of them. You
both
can do the argument. So the other one, the kind of characterizing in terms of positive contact form, what doesn't really matter. The other corollary I'm not going to write because it's not useful for me, but I think it's kind of interesting, is that you can show that there's no symplectic cobordism using this work of Hofer. You can show that this also would tell you that there's no symplectic cobordism from this contact form to the standard contact structure on the sphere, which you can think of this as some sort of symplectic generalization of the non-existence of Anosov flows on the sphere.
Why is it not enough to prove the conjecture you mentioned earlier? So, I mean, if you only have finitely many of such hypertight contact structures, and you mentioned
because even if you kind of fix your contact structures, and even if you kind of like keep them transverse, you can just kind of perturb these kind of contact structures and come out of being Anosov and then landing back in Anosov.
And you don't know there are those two Anosovs are.
We're not sure if those two are kind of the same. Another corollary, which is a very easy observation here, but it turns out to be very important for us, is the following: that now if you have a bicontact structure and this flow kind of in the intersection, and let's say something kind of stronger is happening, and that's to say that this R plus is included in C minus. So let's say this is kind of tangent to your negative contact structure. Since this negative contact structure is always in this quadrant, that automatically would tell you that X is Anosov. And this is an immediate corollary, but it's a nice one, because the condition that we see here, they're just purely contact geometric conditions. You don't really need to refer to this kind of like this kind of quadrant. So this is purely a contact geometric condition, and ideally in this characterization of Anosov flows, we need a condition which looks like this. And the main theorem of my talk is that this is an if and only if situation. And this is basically the condition that would characterize this Anosov flows. Oops. So theorem is that X is basically Anosov if and only if X is included in this bicontact structure. So basically, let me write this. So there exists a bicontact structure such that X is included in this intersection, and C minus. So let's say R plus is included in C minus for some Reeb vector. And now on this side, you have a purely contact geometric condition that makes it kind of equivalent to being Anosov. Another way of thinking about this is that there exists some contact form alpha plus such that, okay, this includes the vector field x, and also the lead derivative of alpha plus in the direction of x is a negative contact form. So that's another way of thinking about this, and this is nice because now you can think of anosovity as some sort of open condition on a one form, on a contact form. So any kind of like H principle or like, you know, it's nice to think of this basically in terms of like just one of the as a condition on one of the contact structures. And also you can describe this as a condition on a Reeb vector field. It's a Reeb vector field for a contact structure containing the flow such that, you know, you have x, r plus, Lie bracket of r plus and x, and r plus in an oriented basis. And a contact form by contact structure or a Reeb vector field with this property, I call that strongly adapted. And the key component of like this terminology and basically like the proof is a refinement of the technique of Hirsch-Kirchhoff and Holmes that we mentioned earlier. So the proof, in short, is that let's say I choose the second kind of characterization. So if I look at this lead derivative, and if I want this to be negatively contact, it's not that hard to see that this is equivalent to the kind of, okay, if I look at the norms induced by this, by alpha plus, and you have some additional condition which looks like this. And here, RU minus RS being positive, this is really like encoded in the bicontact structure. So all you need is to kind of do some sort of process to make sure that these two terms can be arbitrarily small. And this can be done by some sort of refinement of the technique I started with by doing to Hirsch-Kirchhoff. I call this process asymptotic synchronization. And in fact, this process will give you much more than actually what you need in this theorem. So you can make these norms arbitrary kind of uniform, make it kind of arbitrary close to an algebraic kind of model for the algebraic kind of Anosov flows. And this turns out to be kind of like basically inspired by Hirsch-Kirchhoff. That's why I call this a strongly adapted, because all you need is to some sort of enhance that kind of technique and kind of give this additional kind of structure. So if I want to kind of complete this picture, basically you have this condition and R plus included in C minus, and basically you can basically complete the picture like this. Okay. Something that might be kind of useful to notice is that you can actually also characterize incompressible volume preserving Anosov flows. And this was actually done before all of this because you can somehow use the invariant volume form and kind of bypass this argument. And that is when both, if this can be done both simultaneously. So R plus can be, the Reeb vector field of one can be included in the other one, and simultaneously R minus can be included in the other one. So in the last few minutes, can you tell me how many minutes?
Maybe 3 minutes.
3 minutes. Okay, so let me say a few words without that much writing in terms of like the further directions. So one thing that we can show is that the space of these kind of structures, these kind of geometric structures, is a cyclic fibration over the space of Anosov flow. So the kind of map sending such kind of pairing to the vector field is basically a homotopy equivalent between the space of Anosov flows and these pairs, strongly adapted pairs. And that means that the classification of Anosov flows would be the question would be the same as the classification of these kind of geometric objects. Another remark is that these geometric objects can be taken to be arbitrarily smooth. So basically as regular as the flow, which is something we didn't have in the kind of other formulation in terms of foliations. And for instance, also, if you want to think about the existence problem, so if you have a free manifold, then there exists some Anosov flow. If and only if there exists some Reeb vector field contained in some negative contact structure. And the reason for that is that if you have a Reeb vector field with this property, this is going to be transfers to some positive contact structure, and if this is furthermore tangent to some negative contact structure, congratulations, because you just found that some Anosov flow here. So you can kind of translate the existence question also to some existence question for some class of Reeb vector field. And another direction is to use this Reeb vector field to say much more about this about this Anosov flows, because these Reeb vector fields generically, they have, let's say, generically they have like a surface of section. That's not true for Anosov flows. We can use that surface of section. And even in this homotopy equivalent, something I wanted to mention was that, as I mentioned, these contact structures showing up in this construction you have finitely many of them. So this construction can be also very useful for that kind of project. The last thing I want to say is that this also helps us kind of reapproach a lot of like gluing and surgery kind of questions about Anosov flows. So because now we're reducing this Anosov condition to some sort of local kind of geometric condition. For instance, if you want to do some sort of surgery, in order to get some Anosov flow, all you need is to make sure your operation preserves this kind of geometric structure. And that kind of bypasses a lot of technical kind of difficulties that you had in the kind of previous constructions, and also for constructing Anosov flows by kind of gluing pieces of kind of hyperbolic dynamics. That's one very important approach in the classical theory, but it's also very, very technical. It's known to be quite technical. But from the contact geometric viewpoint, if we kind of preserve this condition when we're kind of gluing near the boundary, we don't need to check anything inside these pieces, which is something causing a lot of difficulties in the standard theory. So hopefully this approach will help us kind of reapproach some kind of old and classic questions in Anosov dynamics, and that's why I wanted to tell you about.
Any question?
See, people wanting to some facts about the type of the space of multiple contacts.
Okay.
I was curious if we could do some in some of the spaces probably.
That would be definitely an interesting approach. Basically, here we can, so if you want to, for instance, think about the finiteness question, we can basically fix these contact structures up to isotropy. And in fact, using Gray's theorem, we can even assume that one of them is completely fixed in any kind of homotopy. Now, how do you want to kind of approach understanding this homotopy of like these Y contact structures? There are probably different approaches. One would be like maybe the one you're mentioning. Another way of thinking about this is to think of this in terms of bifurcations of like these sum flows. So even if you kind of pass through a family where you're losing transversality of these kind of contact structures, you get some flow which still has some meaning. So there is some kind of direct dynamical approach of understanding this kind of bifurcations, and maybe there are some other like flow theoretic kind of approaches. I mean, these are all kind of wide open directions.
Is there like, can you say what it means in the language of like symplectic geometry? If you were to look at either symplectic depiction of the space, or to look at, I don't know, if you were to construct a floor manifold with a symplectic structure out of this, what would it?
Yes, so I think the kind of more standard way of kind of thinking about this is in terms of this deal with geometric approach that I mentioned. So if you have, and this is also due to Mitsumatsu, it turns out that if you have some Anosov flow, let's say it's lying in the intersection of this pair, then you can think about some like interval or like R, if you're interested in the kind of non-compact version of this, for manifold, and kind of equip this with an exact symplectic structure such that it kind of restricts to these two contact forms on the boundary. So this is this, and actually you can construct this kind of Liouville form as a linear interpolation of these two. So if you take S to be the parameter here, you can define this alpha as 1 minus S alpha minus plus 1 plus S alpha plus, and think of this as a Liouville form. So in some sense, these two kind of contact forms, they're like semi-fillable. So if you think about this three manifold with alpha plus, and also reverse or in orientation of the same three manifold with alpha minus, which means that this is a positive contact form on minus alpha minus, then you have some sort of Liouville form, Liouville flow is flowing out. And it's, I think, an interesting question to try to understand, use this symplectic manifold or Liouville manifold to say something about like these Anosov flows. And that's actually a more kind of traditional way of kind of thinking about this, the connection between contact structures and kind of Anosov flows. Because if you look at basically the skeleton of this Liouville dynamics, that would be actually a copy of your original kind of Anosov flow. So you have your original Anosov flow somehow kind of showing up on the skeleton, and then the nearby kind of flow lines kind of flowing out. Can we study holomorphic curves here? That would be super interesting. We don't know that much about these things.
Yeah, that would be like a good way to approach that problem.
Yes, something that it makes some kind of trouble is that, somehow we don't really understand what happens in terms of like holomorphic curves, Lagrangians, and this kind of stuff as we kind of pass through this kind of a skeleton. So for instance, if you think about this geodesic flow example, on one side you have the kind of Reeb flow, which is a S1 fibration. And on the other side, you have another Reeb flow, which is equivalent to your original Anosov flow. So in some sense, the Reeb flows on the two sides are very, very kind of dramatically different. And in some sense, we don't really have a nice way of kind of relating the symplectic geometry on the left-hand side of the skeleton and the right-hand side of the skeleton.
So somehow it's like the symplectic geometry, something like something of that should give you a map from some contact homology type thing of alpha minus to some contact homology.
So that's right. I mean, what it's been done so far is to try to kind of use kind of classical invariants like floor theoretic for kind of category of these objects and say that, oh hey, they're also invariants of the original Anosov flow. And that's been quite like insightful in some sense, but also it has its own limitations because first of all, we don't really know what these invariants mean. There's this work of Chilevik, Lazarev, Massoni, and Moreno that they define some invariants like this, but in some sense, they don't really know how they can reveal some information about the underlying Anosov flow. So it's, I think, a good project to try to think and define some sort of, instead of just saying that, hey, any invariant of this object is an invariant of the flow or something like that. It's a better project to try to define some sort of invariant, which is kind of has closer connection to the dynamics of the Anosov flow, so that it can be kind of more revealing in terms of like dynamical information.
Any other questions? If not, let's thank Surena.